In a ring circuit, even with equal and opposite currents in the conductors, the magnetic fields they create do not entirely cancel out. The key is understanding the direction of current flow. In a ring circuit, current flows in one direction around the ring in one conductor and in the opposite direction in the other conductor. This creates two distinct magnetic fields. These magnetic fields are equal in strength but opposite in direction. However, they do not simply vanish. Instead, these two fields combine to produce a net magnetic field. The magnitude of this magnetic field is determined by the amount of current flowing through the conductors and the proximity of the conductors to each other. The closer the conductors are positioned, the stronger the resulting magnetic field will be. In an ideal ring circuit without any faults, the current should distribute itself evenly across the two conductors. This leads to a relatively uniform magnetic field surrounding the ring. However, the situation changes when a fault occurs within the circuit. For instance, if there is a break or discontinuity in one of the conductors, the current distribution becomes uneven. This uneven distribution disrupts the balance of the magnetic fields, potentially causing localized areas of increased magnetic field strength. These stronger magnetic fields can sometimes be problematic, potentially inducing currents in nearby conductive materials or interfering with sensitive electronic equipment. The principles of electromagnetism govern the behavior of these magnetic fields. Ampere's law, for example, describes the relationship between the current flowing through a conductor and the magnetic field it generates. Faraday's law of induction explains how a changing magnetic field can induce a voltage in a nearby conductor. To minimize the impact of magnetic fields in ring circuits, it is crucial to maintain proper circuit design and construction. This includes ensuring that conductors are properly insulated and spaced and that any potential faults are promptly identified and corrected. Furthermore, shielding can be employed to contain the magnetic fields and prevent them from interfering with other devices. Grounding is also essential for safety and can help to reduce the effects of stray magnetic fields. Regular inspection and testing of ring circuits are recommended to detect any signs of wear, damage, or potential faults. This can help to prevent problems before they escalate and ensure the safe and reliable operation of the circuit. In summary, while the currents in the two conductors of a ring circuit may be equal and opposite, the resulting magnetic fields do not necessarily cancel each other out completely. The direction of current flow, the proximity of the conductors, and the presence of any faults all play a significant role in determining the strength and distribution of the magnetic field. By understanding these principles and implementing appropriate design and maintenance practices, it is possible to minimize the impact of magnetic fields in ring circuits and ensure their safe and reliable operation.